In 2.1d, we're going to describe the effect of adding, subtracting, multiplying, or dividing a constant on the shape, center, and spread of the distributions. So basically the SOCs, but not including the outlier. And before we start the notes, just take a look at this example. Here we have a dot plot of 44 pieces of data, and maybe it's like a test score. So here we have the mean, it says here on this computer output is a 16.2, so somewhere in here is the mean. Standard deviation, we have the minimum is an 8 is the lowest, and then we have the maximum is a 40 and so forth. Now, what if there was an error in this data by 13 points on the test scores, and so you had to subtract 13 points from everything? Think about what would happen. If the minimum was 8, and I had to subtract 13 points from that, the new minimum is going to be 0.5, so it's going to move way over here. If the maximum was 40 and you subtract 13, you're going to be at 27, so it goes from 40 to 27. So what happens is look at the old distribution to the new distribution. You're going to notice it just slid backwards, but notice the shape of that, it stayed the same. What happened to the center and what happened to the standard deviation? I can show you right here just on the output. The center would be the mean. You're going to notice the mean went down by 13. The standard deviation, you're going to notice, stayed the same. So let's carry this example over to a multiplication or division error. They're basically saying, what if someone first recorded the 44 pieces of data and they did it in feet and it should have been done in meters? So the original mean was 9.91, it should have been 3.02. Let's look at this. The minimum was negative 16.4, which is going to be right way over here, but it should have been at a negative 5, which is right here. The maximum was at 88.56, which is right here, but it should have been at a 27, which is right here. So this was the distribution they had, which is much more spread out, but it should have been this. So they did a multiplication or division to go from one to the other. So clearly in terms of shape, you're going to notice it's different. Now center would be looking at the mean. We can clearly tell they're different. And the spread, standard deviation, again, we can tell they're different. So just at a high level, if we have a multiplication or division error or adjustment, shape changes, center changes, and spread changes. If you add or subtract from a distribution, the shape stays the same, the center changes, and the spread stays the same. Let's look at a much more specific example and officially start the notes. Now here we have 7 pieces of original data, and I'm going to go ahead and tell you the median, mean, range, IQR, and standard deviation of those. So if you were to compute the median, it's going to be 8. The mean is 9.7. The range is going to be max minus min, in this case 17. IQR is 11, and standard deviation is 6.23. Now, in terms of measurements that were important about, remember the mean and median are going to be our center, and then these 3 will give us our spread information. So let's take a look at what happens. Let's take each piece of data now that we had above here and add 4 to that. So 3 goes to 7, 4 goes to 8, and so forth. Let's recompute the statistics. I will tell you the median goes to 12, the mean is 13.7, the range will go to 17, IQR is 11, and the standard deviation is 6.23. So clearly what we're seeing happening here is that our measures of center have changed, spread did not. Okay, what if we take this same piece of data up here, and now we multiply them all by 3. So 3 goes to 9, 4 goes to 12, and so forth. If we recompute these statistics, we're going to get a 24 for the mean, or median. The mean is going to be 29.14. The range is 51. IQR is 33. Standard deviation is 18.71. So what we're seeing happen here is you're going to see that the measure of center used to be 8, went to 24, so it was times by 3. The IQR was 11, it went to 33. So we actually see here the measure of center and measures of spread all change. Now, what if we do 2 types of transformations? What if we do an add or subtract and a multiply or divide? In this case, let's take each piece of data, multiply it by 2, and then add 3. So if we take this, 3 times 2 is 6, plus 3 is 9, and we do that for each piece of data. Recompute the statistics, and what you're going to get here is you're going to get 19, 22.4, 34 for the range, 22 for IQR, and 12.47. Now, in this case, what you're seeing happening is it just be really thoughtful. When we added or subtracted, the mean and median changed. When we multiplied, the mean and median change, which means this is going to happen, both components are going to take place. If we look at the original measure of center, which was 8, if we take 8 times 2, it's 16, plus 3 is 19. So the measure of center changes just like this. Now, in terms of the spread, what you're going to see happening on here, remember when we went back, spread was not impacted by adding or subtracting, but it was impacted by multiplying. So the only transformation that impacts the spread is the times 2. Well, 17 times 2 is 34. 11 times 2 is 22. So from this, we can make some conclusions. What we saw then is that the median was impacted by either adding or subtracting and multiplying and dividing. So both the B impact and the A. The mean is the same thing because that's a measure of center. Now our spread components were only impacted by the multiplying, so range, standard deviation, and IQR. They are not impacted by the adding or subtracting. Now, if you think about this, what is the effect of adding or subtracting a constant? Remember when we saw those the measurements on that first slide that aren't in your notes, what happens to a piece of data if we add to it, it slides. It's going to move forward. If we subtract, it's going to go back. So adding and subtracting basically is going to slide the data backwards or forwards. So the sliding it forward or backwards is going to cause the center to be impacted into change. Well, what happens to the shape? Nothing, and nothing to the spread. Now, the effect of multiplying or dividing, that does is it stretches or shrinks the data. And if you stretch or shrink the data, the center is definitely going to change, the spread will change, and so will the shape, as we saw in that first slide. You know, what is the effect of adding and subtracting and multiplying and dividing? It's a combination of these two. You're going to have this and this happen at the same time. Now, what can we do? Can we connect the transformation with a z-score? Absolutely. A z-score basically is a transformation. It's a standardization of our data. So remember, this was our z-score in terms of the population information. What we did here is we subtract the mean, which is a slide, and we divide by the standard deviation, which is a shrink or a stretch on the data. So these two components are transformations of the data. Now, this is a nice example where we're just going to go ahead and change the statistics that they've already computed for us, and we're not going to do the crunching ourselves. This right here is a sample of 30 test scores. This is our dot plot. This is the original statistics from these 30 test scores. So we see that there are 30 pieces of data, that's N, the class average is 35.8, standard deviation, and other components. It says here, suppose the teacher was nice and added 5 points to each test score. How would that change these components? So of all of these elements here, what will change and what will stay the same? So N is the number of students in test scores. It's still 30. Adding 5 points, the mean here is going to change, so it's going to go to 40.8. The standard deviation is going to stay the same. Now be careful, the minimum, if it was 12, it will go up to 17. That did get impacted. Quartile 1, does that change? Sure, if 32 was the 25th percentile, now 37 will be, so that does change. The median score was no longer 37, it's now going to be 42. Quartile 3 is going to change to 46. The maximum score is going to go up to 53. Now the IQR stays the same at 9, and so does the range. So in these elements, the things that stayed the same again were the counts of the data, standard deviation, IQR, and range. So that's the spread. The transformation here is they took the piece of data and they added 5. Now, part B of this, suppose the teacher in the example took the original scores Since the test was out of 50 points, he would multiply each score by 2 to make him out of 100. So if he wants to make that adjustment, can he do that fairly easily? How will these test scores change? Well, if you think about the transformation, what he's going to do is he's going to take the 2 times the x's. So everything gets multiplied by 2. So in this table, every statistic changes with exception to the count of the tests and the students. It's still going to be at 30. Everything is going to double to these new statistics. And these will be the new answers. Knowing these shortcuts is vital because we don't want to have to go back through the data, make the data adjustments, and recalculate the statistics. On an AP exam, they're probably not going to give you the detailed data, so you would not be able to use the longer method to figuring out. They want you to use the shortcuts on this data to get the final answers. If you want another quick example, let's do this one. Suppose a class took a 40-point quiz. The results show the mean score of 30, the median 32, IQR of 8, standard deviation of 6, min of 12, and quartile 1 of 27. What happens to each of these statistics? So the first thing is I want to do is to add 10 points to everyone. So this will be x plus 10. Part B, I decide the weight the score is 80 points, so I double. So this is going to be 2x. And then part C, I decide to cut the quiz as 100 points, so I double each score and I add 20. So I'm going to double each score and then add 20. Take a moment, see if you can write down the final statistics for each of these scenarios. So you can go ahead and check your answers. For part A here, we're going to change the mean, the median. The min in quartile 1 will also change, but our measures of center won't. For part B, everything does change. So we're going to change all of these components are going to be doubled from what they originally were. And for part C, we can actually piggyback off of B since this was 2 times x and this is 2 times x. All I have to do for part C is to take the part B and add 20 where it's relevant. Be careful on this. The mean and the median, we do add the 20 from this current score. IQR and standard deviation are going to stay the same here, but the minimum and the quartile 1 will both be adjusted too. Let's look at another example. Suppose a teacher gave a test for which the class average was 72, standard deviation was 21. He wants to apply a linear transformation of A plus BX to scale the grades. So the mean is 82, the standard deviation is 7 for the new. Find out what A and B were. It's actually a little bit of a tricky question. So we know the transformation, what's going to happen in this case. Again, it's A plus the BX. They want us to find A and B for this transformation. One of the connections I can make is I notice here that the original standard deviation was 21. The new one is 7. So what happened is they took the original 21, times it by something, and got 7. If you solve this, you can just divide each side by 21. So 7 over 21, or it's going to tell you that there was a 1/3 change. So on the transformation, if this is the new, I'm going to start to build my transformation right now. It's going to be something 1/3 times x. Now, what's the adding or subtracting? I'm going to have to go look at the calculation to the mean. Now, so the mean went from 72 to 82, so I can actually set up a transformation. The new answer was 82. Now, originally, they took the 72, and I know they had to times it by 1/3, but they're going to add something to that. If you simplify this equation, you're going to get A plus 24, and if you solve this, you're going to get that A equals 58. So I can actually wrap up the transformation. What they did is they took 58 plus 1/3 times the x's to change the mean and standard deviation of the scenario. Last example here, we have taxi cabs in New York City. They charge an initial fee of $2.50 plus $2 per mile. The equation that they used for transformation was this, 2.5 plus 2 times your miles. At the end of the month, the businessman collects all of his taxi cab receipts and calculates some numerical summaries. The mean fare that he paid was 15.45, and the standard deviation was 10.2. And the first question, what are the mean and standard deviation of the lengths of his cab rides in miles? Well, we can just use the transformation that took place here. We know that the mean was impacted by both the multiplication and the adding. So we could say 15.45, what had to happen is 2.50 plus 2 times his miles. And if you solve this equation, we're going to subtract 250 from both sides, divide by 2. The mean number of miles would have been 6.475 miles. Now, to find the standard deviation, the 10.20, standard deviation was only impacted by the multiplication, so it's 2 times miles. If you divide by 2, you're going to get that the average, the standard deviation here, was 5.10 miles. Part B, if the businessman standardized all of the fares, what would be the shape, center, and spread of the distribution? So if we remember, to standardize anything, what you're going to want to do is compute a z-score. So to standardize, we're going to take the piece of data, we're going to subtract the mean, in this case, which is going to be 15.45, and then the standard deviation of 10.2. Now, when you standardize anything, the shape on it is going to stay the same. It's going to be unimpacted for that. But when you do standardize, the center is going to actually adjust. The mean of a standardized z-scores is 0. Because in order to compare data, when you standardize, the new z-scores will be their z-score from the average z-score of a 0. Now the spread, the z-score spread here is just going to be sigma of x is going to be 1. So when you standardize any data, the mean and standard deviation of that new data set or of those z-scores is 0 and 1. And the shape is unimpacted.